Hello everyone, I'm Nitin Sethi from Nainital, India. I have worked in the field of deep learning from 2 to 3 years. So today I'll be teaching you face detection using Haar Cascades. So I'll tell you how would the course proceed. First of all, I'll tell you what are the basics of OpenCV. I'll introduce you to OpenCV, which is mainly used for image manipulation. Then I'll be further telling you how to draw various figures on an image like rectangle, circle, etc. I'll also be telling you how to blur images and a few other functions using OpenCV. Then we'll be learning about Kmeans clustering algorithm and how do we use that in OpenCV. After that, we'll be learning how to reverse a video. That is, suppose there's a video that moves from A to Z, we'll be learning how to reverse it from Z to A. Through this, we'll also be learning how to capture videos, how we'll be learning about frames, etc. Then in the second session, we'll be moving to the theory of Haar Cascade, where I'll introduce you to Euler-Jones algorithm. In that, we'll be learning mainly about 4 important things. The first is Haar features. I'll be telling you what are Haar features. Then we'll be learning what an integral image is. Then we'll be learning about an important algorithm which is AdaBoost. AdaBoost is widely used in Haar Cascade. It increases the computation speed by a large amount. In the end, we'll also be learning about cascading. Then in the third session, we'll be finally moved to the coding part. First of all, we'll be learning how to use a pre-trained Haar cascade for face and eye detection. Then we'll move on to prepare our own custom Haar cascade. We'll be learning how to create negative images, how to create positive images, and how to finally prepare our dataset for the training part. Then we'll be learning how to train our own Haar cascade. In the end, we'll be generating our own XML cascade file from the trained Haar cascade, and then we'll be using that for our custom detection. I hope you enjoy the journey as much as I did making it. Thank you. Hello and welcome. So in this video, we'll be learning the basics of OpenCV. OpenCV Basics. So why are we even learning the basics of OpenCV? The reason is, whenever we are interested to apply face recognition to video streams or to images, or to build a complete deep learning pipeline for image classification, or even if we want to do a very simple task with Raspberry Pi where it is something related to image, even if it's a very small project, we'll most probably need OpenCV. OpenCV is one of the most useful tools for a person who deals with images. So let's start learning OpenCV. So first of all, we learn how to load and display an image. Load and display an image. For that, first we'll import CV2. Then we'll be importing NumPy. So the image that I have is 1.jpg. So we'll be reading that image first of all. We are reading that in a variable called img. So we read that image by img equals to cv2.imread, and then the location and including the name of the image. So this is it. Now we'll display img. So it's numbers. Okay, but we don't want to see numbers. We actually want to see the image. So we'll be learning that also a bit later. So first of all, let's know what is actually the height, width and depth of the image. we learn that by height, width, depth equals to image dot shape. So what does image dot shape do? It returns a tuple with three variables. First is height, second is width, and the third is depth. Height, width, and depth. So now we'll be printing all three. Width is height is and depth is dot format width, height, and depth. So the width of our image is 320, its height is 390, and its depth is 3. But you might be confused that why did I put width first and height later? Why not height first and width later? So there's a reason to that. In NumPy, we describe image matrices by rows into columns. But you must understand that the number of rows is our height and the number of columns is our width. So the number of rows is our height and the number of columns is our width. And what is depth? Depth is the number of channels. In this case, our depth is 3. In NumPy, we represent depth by RGB. But here, the depth is represented by BGR, that is blue, green, and red. So now let's display that image. Display the image. We do that by cv2.imshow image. This is the name of the title and this will be the image. And then cv2 dot wait key, and then in the end destroy all windows. Destroy all windows. Just give me a minute, I'll just show you the image that has loaded. So as you can see, the image has been successfully loaded. So now I'll cancel. Okay. So the next thing we'll be learning is how to access individual pixels in an image. So first of all, what is a pixel? All images contain pixels, which are actually raw building blocks of image. Images are made up of pixels in a grid. For example, suppose we have a 100 cross 100 image. So that will have 100 rows and 100 columns. So there would be a total of 100 into 100, 10,000 pixels in that image. So each pixel is a value from 0 to 255. And whenever we have channels, for example RGB, so the pixels in the R1 would represent how red from 0 to 5, it would represent how red the color is, I mean how dark the color is. So the G would be for green and B will be for blue. And now you'll ask, why is the ordering opposite? Why is it BGR instead of RGB? The reason is because when NumPy started, when NumPy was developed, it was developed in BGR order. That was the standard during that time. But over the time, the standard shifted to RGB. But OpenCV still maintains the legacy, which is BGR, so that no code breaks occur. So that is the reason all the image work in OpenCV is in PGR. So the each value of PGR is a 3 tuple between 0 and 255. So how many color possibilities are there for each pixel in an RGB image in OpenCV? That is 256 of B, 256 of G and 256 of R. So the total possibilities for each pixel is 256 into 256 into 256. So that would be like quite a huge number. And I don't want to like actually calculate it. So now we'll be learning how to retrieve individual pixels, access individual pixels in an image. So what we'll be doing is we'll be accessing pixel at x equals to 145 and y equals to 145. So that would be PGR equals to image, and we are accessing at 145 comma 145. Now we'll print the values of P, G and R. So the value of R is 142, the value of G is 130 and the value of P is 90. So as we saw, the width was 320 and the height was 390. So we cannot access these above 320 and 390. So now we'll be learning how to slice array and crop them. Extracting ROI, that is region of interest, is very important for image processing. For example, suppose you want to find a face in an image. So first of all, you will be finding that face. Now the next thing, suppose you want to find eyes in those image. So to reduce computation and increase accuracy, you won't be finding the eyes in the entire image. What you'll do instead is you'll slice the eye, you'll slice the face, and in that face you'll be finding the eyes. So let's learn how to slice images. Array. We do that by ROI equals to image. Now suppose we want to slice this. So once we have sliced, we'll be showing it cv2.imshow ROI, ROI cv2.weight key 0, and in the end cv2 destroy all windows. I'll press. So as you can see, the ROI is being displayed now. So this is the part that we've actually sliced. So the next thing that we need to learn is how to resize images. Resize images. Resizing is also important because many times we need to the image is too large and we need to decrease the size, or many times we need to convert the image into a square. So then resizing would be useful. And also image processing is actually faster on smaller images because there are fewer pixels to process. And when you're using deep learning, we actually need to increase the speed of our process. So let's resize. Let me check what was the original size. So the original size was 320, 390. Let's resize it to 200, 200. So we do that by resized equals to cv2.resize image, the image that you want to resize, and what value do you want to resize it to. Now let's display this image. cv2.IamShow cv2.waitKey cv2.destroy all windows. So this is the one that we've resized. As you can see, the original image was quite big. This was like too big, and the resized one is almost half of that. So now we'll learn how to rotate an image. Rotating an image. So to rotate an image, first of all we need center, about what center we want to rotate. So that would be W by 2, H by 2, M equals to. Now we'll get a rotation matrix. We want to rotate it by minus 45 degree. This is the center. This is the angle by which we want to rotate, and this is the scale. So rotated image will be cv2.warp-affine image M and WH. Now we'll show that image. wait key, destroy all. Center, okay. M is not defined, okay. Okay, so as you can see, the image has been rotated. It was straight, now it's like this. So what we did in rotation, we calculated the center about which we want to rotate. We used this double because we want to perform integer maths, not floating point values. Then we calculated a rotation matrix where minus 45 means we want to rotate it by 45 degree clockwise. We can use some other value also depending on how much we want to rotate. So the positive angles are anti-clockwise and the negative ones are clockwise, and in the end we'll warp our image to this, and then we show our let's rotate it 45 degree positive also once. So as you can see, this time it's rotated 45 degree positive. So this is how we rotate an image. So now we'll be learning smoothing an image. In many image processing pipelines, we must blur an image, and we do that to reduce high frequency noise, and this makes it easier for our algorithm to detect and understand what are the contents of the image. So the algorithm won't be confused with the noise. Blurring an image is quite easy in OpenCV, and we learn one of the ways. We'll be using Gaussian blur to smooth an image. So let's start smoothing. Let's learn how to apply this Gaussian blur. Smoothing an image. So we'll be doing cv2 dot Gaussian blur our image, and then the kernel, and then 0. So we have applied a Gaussian blur with the 11 cross 11 kernel to the image, which is img. If we would have applied larger kernels, the image would have been more blur. Small kernels create less blurry images. I'll just write it down. 11,11 is the kernel. Larger kernels correspond to more blurry images. So now we'll be showing it using cv2. We'll be doing cv2.imshow blurred cv2.waitKey 0, and then cv2.destroy all windows. So as you can see, the image which has come, it is quite blur. So let's try with a larger kernel. So as you can see, when we increase the kernel size, the image became more blurry. So this is how we use CV2 to blur an image. Now the next thing that we learn is how to draw a rectangle. Suppose we want to draw a rectangle in an image. So how do we do that? Drawing a rectangle. A rect image equals to I'll copy the image first, and now we'll draw a rectangle. We want the rectangle on rect image, and now we'll give the top left coordinate of the rectangle, top left corner coordinate of the rectangle. So we can give anything. Let's give 22 comma 22. Then we'll give the bottom right corner coordinates of the rectangle. Let's give 90 comma 90. Then 0 0 2 to 5, and 2. So this was the image on which we'll be drawing rectangle. This is our starting pixel coordinate, which is top left. This is our ending pixel, that is bottom right. This is the BGR tuple. This 0 0 2 to 5 represents red. We want the rectangle to be red in color, and by 2 we mean thickness of the rectangle. If we would have supplied a negative value like -1 or -5, that would have made a solid rectangle. Now CV2 dot I am sure rec image CV2 dot wait key, and then CV2 dot destroy all windows. So as you can see, there's a rectangle in our image. Now let's change the position a bit. Let's make it 122 comma 122. So as you can see, the rectangle is now in between. So it's red in color. I'll also show you with a negative value how does the rectangle look like. So as you can see, whenever there's a negative value, the color will be filled inside. It would be a solid rectangle. Now the next thing that we'll be learning is how to draw a circle. Drawing a circle. So we'll do the same. Circle image equals to image dot copy. We draw circle by CV2 dot circle image 120 comma 120 comma 40 comma 0 0 2 to 5 CV2 dot I am show circle image CV2 dot wait key and then cv2 dot destroy all windows. So now as you can see, we have a circle on our image. So I'll tell you what are the parameters. So this is the image on which we want to draw a circle. This is the circle center coordinates. So our circle center would be at 120, 120. Then 40 is the radius of circle in pixels. So this is the circle radius. So for us it's 40 pixels. Then this is the color, circle color, and this defines the thickness. Similarly, even if we have a negative value here, we'll see the circle is a solid circle. So this is how we create a circle in CV2. The next thing we'll be learning is how to create a line in CV2. Drawing a line line image will be image.copy cv2.line line image (200) comma 2 dot cv2 dot destroy all windows. So here this is the image over which we want to draw a line. This is one of the points, the starting point on the line, and this is the point where our line ends. So a line will extend from point 120, 120 to 200, 200. This will be the color of a line and this would be the width of a line. So let's run this now. So as you can see, we have a line. So when we increase the width, we'll have a line with a bigger width. So I'm just curious, let's see if it runs with a negative value and what do we get. Okay, it's not running, fine. So this is apt, this should only happen. Now the next thing that we'll be learning is how to put text on an image. Many times it happens that we want to have some text overlay over our image. It is very important many times during object identification, etc. tasks. We want to overlay text on an image. For example, like even if we are working on face recognition, we'll want the name of the person above their face. Or if you're building a classifier or an object detector, even then we'll want the text on over that image. So we'll be learning about PutText function. So we copied the image. Now we'll be using PutText function. Now we'll be telling which font do we want to give. So we'll be giving a simple font Hershey Simplex 0.7, 5. Now we'll be showing the image. And then in the end we'll destroy all windows. So as you can see, now there's text over the image which says welcome to live edu. So this is the image over which we want to overlay the text. Now this is the string of text that we want over the image. This is the actual text. This is the point of starting point for the text. This is the font of the text, the font that we want our text to have. After that, this is the font size multiplier. This is the text color, and then we have the thickness of the stroke, and that is in pixels. So this is how we use PutText function. So now we learn how to convert an image to grayscale. So you'll ask, originally the image does have a color which is BGR. Why do we want to lose information? Why do we want to convert the image into grayscale? So the answer for that is, many times we want to downsize our image, I mean decrease the size of our image, so that it processes faster through a neural network. So turning a colored image into a grayscale image is a very good option then. So let's convert our image to grayscale. Converting an image to grayscale. So as you can see, the image does have text at present. So after we convert, it should not have text. So we'll use cv2 dot cvt color image, and then we'll apply cv2 dot color underscore bgr to gray. So now this gray image has a gray color. So let me show you. Then we'll apply wait key, and then Destroy all windows. A gray image. So as you can see, our image has now lost its color and it's gray. So I'll also show you something. Image.size. So as you can see, the size of our image has reduced by like 1/3. That is because it has lost color. So now if we put it in a neural network, it would process faster. So the next thing now we'll be learning is how to detect edges. Many times we want just the edges of an object. We don't want the complete object. So let's learn edge detection now. Edge detection. For edge detection, we use a function called canny. So we learn this cv2 dot canny, and we want to apply edge detection over our gray image 30 and 150. So here what exactly is 30? 30 is the minimum threshold. So we've given minimum threshold as 30 and 150 is the maximum threshold. So now we'll see the image. I am show edge, edge. Dot destroy all windows. So as you can see, now we have an image which has just the edges. So I'll show you what happens when we increase this. So as you can see, the edges have decreased a bit. So that is because we have increased the minimum threshold. So in this we learned how to detect edges. Hello everyone. So now we'll be learning K-means clustering. So what is K-means clustering? K-means clustering is a type of unsupervised learning which is used when you have unlabeled data, that is data which does not have categories or groups. So the goal of this algorithm is to find groups in the data with the number of groups represented by the variable k. For example, suppose you have a large data and you want to find similar types of data and you want to make 5 groups. You want that one of the each group should have similar type of data. So that is the case when you use k-means clustering. So this algorithm works iteratively to assign each data point to one of k groups based on the features that are provided. The data is clustered based on feature similarity, and the results that we obtain of k-means clustering are: 1. The centroid of k cluster, which can be used to label new data, and second, labels for training data. That is, each data point is assigned to a single cluster. So out of, if suppose we had 20 data points, so all of the 20 data points get a cluster, become part of one of the k clusters. So now we'll be learning about k-means clustering in OpenCV. K-means clustering in OpenCV. So first of all, consider that we have a data with only one feature. So let's start creating that data. Is it not? Kmeans clustering OpenCV. Okay, never mind. So let's start creating data. First of all, we'll import the required dependencies, which is NumPy, and we'll be importing CV2, and we'll be importing matplotlib, which is used to represent data. Now let's create some random data. X equals to numpy dot random dot randint 25 100 comma 25. Y equals to numpy dot random dot randint 175. Now we'll create h stack. Z equals to, we'll stack both x and y. Numpy dot h stack so our x is this, y is this, and z is this. So once we have this, we'll reshape z. So now the total elements of z are, we'll reshape z, z dot reshape, we'll reshape it to 50 comma 1. So now the new z is this. Now we'll convert z to float 32. Now we'll plot this on a histogram. plt.hist z 256 and then plt.show. So now as you can see, we have a histogram. So as you can see that z which has a size of 50 and the values are ranging from 0 to 255. So now we'll apply the Kmeans function. So we'll apply the criteria in Kmeans that either when 10 iterations of algorithm ran or we reach an accuracy of epsilon equals to 1.0, we'll stop the algorithm and return the answer. So whatever comes before, the algorithm should stop. So first of all, we'll define criteria. So this criteria will tell when the algorithm will stop. cv2 dot term criteria underscore EPS plus cv2 dot term criteria max iteration. So it tells that either, so cv2.term criteria EPS tells that we need to stop the algorithm if the specified accuracy is reached, and cv2.term criteria max iter tells stop the algorithm after the specified number of iterations. So when any of this condition is met, it will stop. Now we'll give the maximum iteration and we'll give the epsilon. Epsilon means the accuracy. Now we'll give flags. That is just to avoid line break in the code. Now it's time to apply Kmeans algorithm. Apply Kmeans. So the Kmeans returns a tuple of 3 values. The first one is compactness, the second is labels, and the third is centers. So what is compactness? It is the sum of square distance from each point to the centers. What is labels? This is the label array, same as where each element is marked 0, 1 or whatever is the label. And center, it is the array of centers of clusters. So we'll get these 3 values. So I'll repeat, we'll get compactness, we'll get labels, and we'll get centers. cv2.kmeans. Now we want to apply Kmeans to Z. And we want the value of K to be 2. We aren't giving any best labels. We are giving the criteria that we have already defined. Attempts will be 10. And then in the end we'll give flags. So now we have compactness, labels, and centers. So let's see what compactness is. Oh, sorry, I made a mistake in spelling, but never mind, it can still run though. Okay, so this is compactness. Let's see labels. So these are the labels. And in the end we got centers. So these are the centers of those. Now we split the data to different clusters depending on the labels. So we'll split data into 2 parts, A and B. So A will be where labels is 0 and B will be where labels equals to 1. Now we'll plot A in red and we'll be plotting B in blue color, and the centroids we'll plot as yellow, so that we are able to properly differentiate and get an idea. A as red, B as blue, centers in yellow. So this is splitting data depending on their labels. So we'll apply plt.histogram. We want A 256 0, 256, and the color will be red. Now plt.hist B 256 0, 256, and the color will be blue, and then plt.hist centers 32 0, 256, and the color will be yellow. Plt.show. Okay, so now we have the histogram. As you can see, it has split data into two parts. One is this cluster and the other is this cluster, and these are the centers of those clusters. Now the next thing that we'll be learning in the same is data with multiple features. So the first thing that we learned is normal data when there's only one feature. Now we'll be learning when there are multiple features. Data with multiple features. So this was data with one feature. So we have already imported the required dependencies. Now let's make another x and y. X will be equal to numpy dot random dot randint 25, 50, 55, 2. So this is low, this is high, and this is the size. Then we'll give y numpy dot random dot randint 60, 85, 25, 2, and then z will be numpy dot vstack x, y. So this vstack stacks array in sequence vertically. So this will be our z. Now we'll convert z to float 32. Z equals to numpy dot float 32 z. Now we'll define criteria and apply k-means. This will be like same as we did before. Define criteria and apply k-means. So criteria will be cv2 dot term underscore criteria underscore EPS plus cv2 dot term underscore criteria underscore max underscore iter, comma maximum of 10 iterations, and x we want accuracy or epsilon to reach 1. Now we'll get these. cv2 dot k means to applied to z divided k will be 2, none, criteria 10, cv2 dot k means underscore random underscore centers. Now we'll separate the data. But before separating, first of all, we need to flatten it. So we'll use revel function to flatten it. Label dot revel equals to 0 and b will be z of label dot revel equals to 1. Okay, but before, let's see what actually these three are. Ret is this. Label is this. So it has divided 1, 0. And then the third center is this. Now we'll divide it into two parts. Now we need to plot the data. So we'll be using scatter plot this time. Since we have 2D data, plt.scatter plt.scatter b colon comma 0 b colon comma 1, color will be red, and then plt.scatter center size will be 80, color will be yellow, and marker will be S. Marker will be S. Now we'll label the scatter plot plt dot x label. So on x we have height, or I'll rather say feature 1 and plt dot y label will be feature 2, and then in the end we'll show a scatter plot. So as you can see, our data has been like very beautifully split into two parts. The first part is this and the second part is this. We also have centers as yellow. So now we learned how to use K-means clustering with data with one feature and data with multiple features. The next we'll be learning is color quantization. So what is color quantization? It is the process of reducing number of colors in an image. So that also is done by applying K-means to the color. So why do we reduce the number of colors in an image? We reduce that to reduce the memory, and sometimes some devices also have limitations such that it can produce only limited number of colors. So in that case also color quantization is performed. So the color quantization won't be like very different. This time there are three features, that is R, G and B, and then we need to reshape the image to an array of m cross 3 size, where m is number of pixels in an image. And after clustering we apply centroid values. It is also RGB to all pixels, such that resulting image will have a specified number of colors, and then we'll reshape it back to our original image. So let's start coding now. Color quantization. So first of all, we'll be reading the image. Image will be cv2.imread. So let me check if we have some image there. Okay, so we have an image that is 1. The name of that image is 1.jpg, but it does not have a large number of colors. So let's find a new image which has like good amount of color. Nature images, and we also need a jpg image. jpg. Okay, let's try man in nature. Okay, so let's take this image. I'll save it. So we'll read 2.jpg. Now we'll reshape this image. Then we need to convert to numpy.float32. This is like almost same. Then we'll define our criteria. Criteria would also be same. In fact, I'll actually copy the criteria part. Okay, let me copy this also. So the criteria will be same, and then let's define a variable called k, that is 8, and here we'll give k. So that means we want it to split into 8 equal parts. We want k to be 8 actually. Now we need to convert it back to uint. Center will be numpy.uint 8 center. This will be center label dot flatten. So this will be res dot reshape image dot shape. So as you can see, it is like entirely similar. cv2 dot im show res to cv2 dot wait key, and in the end cv2 dot destroy all windows. Okay, so now I'll run this. I has no attribute u. Okay, u int 8 of 100 into shape. Okay, let me check. Okay, never mind, let's not reshape, let's directly show if it does. Now the size isn't perfect. Okay, let's print image dot shape here. 174 to 93, 174 to 93. Cannot reshape array of size 100 into shape this. Okay, okay, let me try running this. Yeah, so it's working fine. So as you can see, our image has been split into 8 different colors, and so this is how we apply Kmeans to our image. So this is known as color quantization. Hello and welcome back. So the next thing we'll be learning is how to reverse a video. So I'll show you the video first. I'll play it. So this is the actual video where the cartoon is moving from right to left. So we'll try to reverse it using OpenCV, and on the while coding we'll also be able to grasp more concepts of OpenCV. So this was the video. So let's start working. Let's start coding. First of all, we'll import the required dependencies, which is obviously CV2, import CV2. Then we'll make a capture object where we'll capture the video. So the name of that video was jump animation.mp4. So I'll enter that here. CV2 dot video capture, and the name is jump animation.mp4. Now we'll read it. So check comma vid equals to cap.read. So the next thing that actually how many images or how many frames are there, and we'll have to like save each frame, so that will also be used for naming. So first of all, counter will be 0. Then we want the initial value of check to be true. We'll also be making a frame list. This is a list that will store all the frames. So once we are done with this, now we'll start saving all the frames. So this will run till check equals to true. cv2.imWrite. imWrite is used to save a frame %d dot jpg counter comma wait. So this will read the next frame, and now we'll append the frame to our frame list, and in the end we'll increase the value of counter by 1. This will take a little time as it will save like many images. So it's saving images. So once it runs, let's see how many images does it actually save. So it's still running. Okay, so it ran fine. So now let's see what is actually the length. Frame list. So it saved a total of like 384 images. Yeah, so that is from 0 to frame 383. Now we'll pop out the last image. Now first of all, we'll see the images or the video in the right order. So for that we'll write for frame and frame list cv2.imShow frame comma frame seal2 dot weight. I'll write a bigger weight key so that it's a bit slower. 0xff equals to of q, it will break, and in the end we'll cap dot release, and then we also need to destroy all windows. seal2 dot destroy all windows. So now I'll run this. Okay, frame is not defined. Okay, it had to be small. Okay, so I'll run it again. So it ran fine. Now we'll reverse the order. For that, first of all, we need to reverse the frame list. Now we have reversed the frame list. Now it's quite easy. We'll do the same for same as above. Cap dot release and destroy all windows. Now I'll run this. So as you can see, this time the object or the cartoon is coming from left to right and it has reversed. So this is how we reverse a video. I hope you enjoyed this. Hello and welcome. So now we'll be learning the basics of Haar Cascade. The main algorithm behind this was Viola-Jones face detection algorithm. It has mainly 4 parts, which is Haar features, integral image, ADA boost, and cascading. If you manage to understand these 4 concepts, you can easily understand Viola-Jones face detection algorithm. So now we'll move to start understanding these 4 parts. So in Viola-Jones face detection algorithm, what are Haar features? Before that, let me introduce you to edge detection. As you know, this is a convolutional kernel with the top line as -1, -1, -1, -1, and the bottom row as this, and the middle row is 2 to 2. When we convolute this over an image, we'll get edges. So this will give us edges. Similarly, if the convolutional kernel is -1, -1, -1, and 2 to 2, and -1, -1, -1, the edges will be a bit that way. So depending on different values of convolutional kernels, we get different features. So these will mainly be used in Haar features. So Haar features are similar to these convolutional kernels, and they are used to detect the presence of features in these images. For example, suppose we take these 5 Haar features. What we'll do is, first of all, we'll take this feature and we'll convolute it over this image one by one. Then after that we'll double this. This is single, we'll double it, like we'll add more white and more black, and then we'll convolute that over an image. and then we'll increase its size further and convolute that. So we'll do the same with all of these different types of half features. In the end, we'll get a single value. What we'll do is we'll be subtracting the sum of pixels under white from under black. So we'll be adding all the pixels under black minus all the pixels under white, and we'll be getting a single value. So as you can understand, like when we use this one over eyes, so this will be able to identify that this region is dark while this region is light, and similarly here too, this region would be dark and this region would be light. So these are known as half features. So Euler-Jones algorithm uses a 24 by 24 window as the base window size to start evaluating these features in a given image. So if we consider all the possible positions, scales, type, there are more than 160,000 features. As you can see, like we'll be using these of different sizes and we'll convoluting them, and we'll be using all of these. So they'll make a lot of features, that is more than 160,000. So since it's clear that huge number of these use the computation rather than summing up all pixel values under the black and white every time, they have introduced the concept of integral image to find the sum of all pixels under a rectangle with just 4 corner values of the integral image. So what is being done is, for example, suppose this is an input image. For an input image, what we do is we find the integral image. So what is an integral image? Integral image has the sum of all the values of pixels which are above that particular pixel and towards left. For example, for this particular pixel there is no value above or left, so its value would be 1. For this there is 1 to the left but no above, so value would be 2. Similarly, for this we'll add these 3 and value would be 3. As you can see, for this these all are above and to the left, so the value would be 9. For this, the above ones are these and towards left are these all. So 1, 2, 3, 4, 5, 6. So this value is 6. So this is how we obtain an integral image. Using integral image, we don't have to sum the pixels again and again. So this decreases our computation time and increases our speed. So suppose we want to calculate the sum of all pixels in D. So what we do is we calculate the sum of all this, then we subtract. Okay, I'll show you one by one. So what we do is, suppose we want to calculate the sum of all pixels in this. So what we'll do is we'll take the value of 4 and we'll add 1 to it and we'll subtract 2 and 3. So what it will do is, here 4 is the sum of all these, 1 is this, so 1 plus 4 will be this all plus this one extra, and when we subtract this, this will go and this will go, and when we subtract 3, these 2 will go. So the extra one will go. In the end we'll be left with just with D. As you can see from this also, 1 is A, 4 is ABCD, 2 and 3 are, 2 is AB, 2 is AB, and 3 is AC. So when we subtract, we just have D left. So this decreases the calculation. So now we have learned what are half features. These are all half features. We have learned what an integral image is. Integral image is very important. These two concepts are like quite important. So now we'll be learning the next algorithm, which is AdaBoost. We'll be learning that in the next video. So now we'll be learning AdaBoost. As I told in the previous video, there can be like 160,000 plus features within a detector of 24 into 24 base resolution, and we need to calculate so many features. But we need to understand that of these 160,000, only a few set of features would be useful. For example, when we detect an eye, this feature would be quite useful as the color tone would be quite different, but this feature would be mostly irrelevant. So AdaBoost is the algorithm which helps in finding only the best feature among these 160,000 features. After these features are found, a weighted combination of all these features is used in evaluating and deciding any given feature has a face or not. Each of the selected features are considered okay to be included if it can perform better than random guessing. So what we do is, after we take all these features, we'll include only those that perform better than random guessing, and we'll make a function. For example, suppose this is one of the feature, this is another feature, and this is third feature. We'll be summing up all those features and the sum would be a weighted sum. We'll weight by some quantity which we'll learn how to find later, and we'll be using this to make a strong classifier that will detect our image. So I'll tell you how does AdaBoost work. So suppose these are positive features and these are negative ones. So what AdaBoost does is, first of all, it gives a uniform distribution over weights over all the training examples. Now suppose we select a classifier with the lowest weighted error, the one which classifies most accurately. As you can see, it has classified almost correctly, though these two are wrong and this one is wrong. So now what we'll do is, we'll increase the weights of those which are wrong, and we are doing this so that the next classifier focuses more on the ones which are wrong. So we have increased the weight, and the next classifier decreases, removes these two. But as you can see, the others became wrong. So this process will keep on repeating, and in the end we'll have a carefully made linear combination of all the weak classifiers. As you can see, if it's in this area, then it's positive, otherwise it's negative. This is how AdaBoost works. So also AdaBoost finds the single rectangular feature and threshold that best separates the positive and negative training examples in terms of weighted error. So for what it does is, it gives more importance to the ones which are wrong. So first of all, suppose we'll run one of the classifiers over all these images, and suppose a few are wrong. So the next classifier would make sure that it corrects the ones which are wrong. It is also like a Gaussian weak classifier. So this is the algorithm for AdaBoost. It starts with random uniform weights, as we just told. Then after that we normalize the weights. Then an error is evaluated. So hi x minus yi would be 0 for all the ones where there's no error, but it would have some value where there's error. So then we'll update the weights. The weights would be more for the ones where there's an error, and this would go on until we have a strong classifier. So final classifier would be the combination of weak ones, and they'll be weighted according to the error that they had. So the basic principle of this algorithm is to scan as many times to the image, and each time with a new size. Even if an image should contain one or more features, it is obvious that an excessive large amount of evaluated sub-windows would still be negatives. So now we are learning about cascading. So what cascading actually is, even though in Viola Jones we learned so many features, even then we can be clear that like when we apply a particular feature, we can be clear that to a large extent we don't need, suppose Ada Boost found in the end that there are like 100 features which are actually useful, but when we actually when we actually apply those features, we can in just like 10 of with just 10 of the features or 12 of the features, we can be like definitely sure that this does not have the image that we want to identify. So ADA cascading is used for that. So a cascading is composed of stages. Each contains a strong classifier. So what it does is, suppose stage 1, it divides into stages. So suppose stage 1 would have 4 features, stage 2 would have 8 features. So an input would come, an input image would come. Suppose this stage 1 would be able to directly identify that whether this definitely does not have an object or it might have an object. So this way, all the images that go through this pipeline, that means which do not definitely don't have an object, we don't have to process them further on other, yeah, we don't have to process them further. So that way we save a lot of computation. So to design a cascade, we must choose the number of stages, how many stages we want, number of features each strong classifier should have, and a threshold value of each strong classifier. So since finding optimum combination is extremely difficult, Euler Jones suggests a heuristic algorithm. It says that we need to manually tweak. It says that decide the maximum acceptable false positive rate you want per stage, minimum acceptable true positive, and target overall false positive, and according to that you need to keep adding more and more stages. So this is the algorithm for cascading. So now we'll see how exactly it does. So for training set, and images would come, they'll convert into integral representation. So after that we'll have a feature computation. Then Ada Boost feature selection would have stages. As you can see, there are various stages. So now images would go, first of all the image would go to stage 1. It would either be accepted into stage 2 or it would be rejected, saying that it does not have an object. So for example, this one, it identified phase. So summary, so the phases would come, a train cascade of classifiers and Ada Boost would be used, and then it would be applied to each window. So here we learned how half features work, how integral images work, how Ada Boost work, and how cascading works. So now we'll be using Haar Cascade for face and eye detection. For this we'll need a cascade file, which is Haar Cascade underscore I dot XML and Haar Cascade underscore frontal face underscore default dot XML. I am assuming that you already have that file. If you don't, you can go to this link, which is OpenCV, which is this github.com /OpenCV /tree /master /data /Haar Cascades. Here you will find Haar Cascades for various objects, for example eye, for upper body, for smile, for nameplate, for faces, for full body, and various others. I've already downloaded the file, so I'll be using that XML file. So let's start coding. First of all, we'll import the required dependencies. Import required dependencies. So we'll need to import NumPy and we'll need CV2. Import NumPy, import CV2. After that, we'll need to make a cascade classifier object. For me, my cascade classifier object is in C users, user, Anaconda 3, library, site packages, CV2 data, and Haar Cascade file. That is the address for me. I suppose your two might be there, or you can actually find where it is for you. So I'll first of all I'll make a face cascade. CV2 dot cascade classifier. So this is my frontal face, the location of my face cascade. The name of this file is Haar Cascade frontal face underscore default dot xml. You can download it from here if you don't have it. Frontal face underscore, yeah, it is frontal face underscore default dot xml. This one is the file. It's not working for me. Another thing that you need to make sure is this should be, the backslash should be double, or you can actually write R before that. And other than that, we'll make an I cascade to detect our eyes. The process will be same. CV2 dot cascade classifier, then the address. The name this time is different. Let me check the name. So it is Haar Cascade underscore I dot xml. So we have made our cascade files. So now I'll make an CV2 dot video capture. So this will be used to capture video, and the video will be inside that cap object. Now we'll make a loop while true. Comma image will be, we'll read the cap. Here we made cascade classifiers. So here we are capturing video. So here we are looping over all. Here we are reading into our image. So now what we'll do is we'll convert the image that will be captured here will be in BGR format, that is blue, green, red format, and so we'll convert that into gray format. So we'll use gray equals to CV2 dot CVT color. It is used to convert color, and we want to convert our image, and we want to apply CV2 dot color underscore BGR to gray. So this will change our color of the image to gray. Just give me a minute. Converts into gray image. So once we have done that, we'll be using face detect multiscale. So we'll be using faces equals to face cascade dot detect multiscale, and we want to detect gray, and we'll be giving 1.3 and 5. So now faces will have 4 coordinates, which is x, y, w and h, where x and y is the x and y coordinate of the detected part. Like suppose it would have detected the face as a square box, so x and y would be the top left coordinates of that square box, and w comma h, or the third or fourth index of faces, will be the width and height of image. So now we'll be making a rectangle around our image. So for that, for x comma y comma w comma h in faces, cv2 dot rectangle. So this will make a rectangle, and we want a rectangle over this image, and the coordinates will be xy comma x plus width and y plus height, and this will be the color of the rectangle, and the width will be 2. Yeah, the thickness will be 2. So this will be the image, then first point, second point, then the color, and then the thickness. Now we also need to detect our eyes. As you know that our eyes would always be in the face. So eyes cannot be outside of face. So what we'll be doing is, we'll be using only the face part. So it has detected the face. Now we'll be taking in the face as the image, and over that we'll be detecting our eyes. So for that we'll make an ROI gray, that is x plus w, and the ROI color would also be same, image y x So now we'll be doing this the same, but we'll be doing over I. So I's will be I underscore cascade dot detect multiscale, and that will be over ROI gray. Now we need to make a rectangle. So we loop over eyes, and eyes. Now we'll make a rectangle. We want a rectangle over RY color, and the coordinates will be EX, EY, and the other coordinate will be EX plus EW, EY plus EH. And let's make this time of a bit different color. So we'll be doing it 0, 2 to 5, 0, and the width would be 2. So this would make a rectangle over our eyes. So now we want to show our video. So we'll be doing cv2.imshow image. So this we are doing so that if we want to break, so it would be useful. In the end, we'll release our cap and then we'll destroy all windows. All those. So this was face and eye detection using Haar Cascades. So let's run this now. Time to run. Just give it a minute. Okay, so it has loaded. Let me show you also. So this is the, as you can see that it is correctly detecting my eyes. Even if I am moving, it's able to detect, and it's also detecting my face properly. So this is how we use face detection, and we are also detecting eye using Haar Cascade. Okay, so now I'll close it. Hello and welcome back. So now we'll be learning how to create negative images. So to create negative images, first of all, I'll introduce you to ImageNet. Just give me a minute. So what exactly is the ImageNet? ImageNet is like a bulk of images. I'll just show you once. It is an image database organized according to WordNet hierarchy. Okay, so we can since it's negative dataset, we can download anything. For this, will be downloading people dataset. Go here. Just give it a minute, it's loading. Once it loads, we'll get a link. Okay, click download and then you'll get URLs. So click that. So now we have a list of all the URLs where our images are located. So we have a total of, I'll just tell you, we have a total of 1431 images as of now. Let's see how many of the images are of actual use to us. So we'll just need this link for this task. Okay, now let's start coding. First of all, we'll be importing urllib.request download images. We'll be importing the required dependencies. Required dependencies. urllib.request. Then we'll be importing CV2. Then we'll be importing numpy as np, and in the end we'll be importing os. Okay, yeah, it's fine now. So once we've imported these required dependencies, now we'll make a function that stores raw images. Stores raw images. So we'll be using this to download all our images. First of all, I'll give it a link, negative images link. This is the link to where all our negative images are located. That is this. That is the URL. URLs are located here. We need to make sure that all of these are actually double slashes. Now we'll be opening this URL, reading it and then decoding it. So we'll be doing that by negative image URLs equals to urllib dot request dot URL open, and which URL? Negative images link dot read dot decode. Then we'll giving a number. This is just a, so now if not os dot path dot, so we'll be storing all our images in a folder called negative nega nega. So if there's no folder, actually we don't have this folder now, so this will be making the folder. Make if for I in negative image URLs. So now we will be splitting all the URLs by \n. So this means, so negative image dot and negative image URL stores all this data. So once we split it by this, that means \n means next line. So we'll be getting this, then the next line, then the next line, and so on. After that, we'll be doing try, and in case there is an exception, then we'll be printing string E. First of all, we'll be printing which exact URL is this. Then URL lib dot request dot URL retrieve I hit a backslash. So our images will be stored as in folder nega, and the name would be 1.jpg, 2.jpg, and so on. That is the reason this pic underscore num variable we are using. Dot jpg. After that, image equals to cv2 dot so now we'll be reading this image and we'll be reading as grayscale. Grayscale, okay, here it is. Now we want all our images to be of same size, so we'll be resizing them. So resized underscore image equals to cv2 dot resize image, and we'll be resizing it to 100, 100. Now remember one thing, this resizing should be larger than our samples or our positive pics, because we'll actually be placing those positive pics on this image, on these images. Now we'll be saving that image, cv2 dot I am right. Now we'll be doing pic underscore num plus 1. So now we have saved. Now we'll be running this. So we'll be running stores underscore raw underscore this. Okay, let me invalid syntax, except exception as that should be fine. Okay, now we'll be running this. Function object has no attribute decode. read has an attribute decode. Okay, I think I got it. Yeah, it should run now, I think. Okay, so our function has started storing the images. As you can see, it's storing them one by one. I'll also show you in the folder. So as you can see in this folder, it is storing one by one, and so now it will store all the images. So this is how we are storing negative images. For me, I chose persons, I chose people. You can choose anything if you according to your needs. Anything should work fine. Just make sure to resize them because we want of one size and we want them to be at least a bit smaller so that our training is faster. Welcome back. So for our positive images, what I did was, for me, I'll be detecting the cap of the bottle. You can detect whatever object you would want to. So what I did was, I used my webcam to take 4 snaps of the bottle of this cap. So once I'm done with this, what I did was I opened that with paint and cropped the cap of the images. So this is the object that we are actually detecting. So now the coordinates are 0 comma 0 and max comma max. So it would be comparatively easy for us. So after that we need to convert it to BMP format. So to do that, what you can just open it with paint and then save as uh, and then change the format to .bmp. So that should be done. So now we need to resize the image. So for that, first of all, let's resize the image. So we'll open Jupyter. Okay, just give me a minute. So our Jupyter is open. So let me just show you once. Okay, I suppose I'll have to open it with Chrome. Just give me a minute. Okay, so now we'll be resizing our images. So for that, Okay, so yeah, okay. So first of all, I'll be making new Python. Resize image. Resizing image is comparatively an easy task. First of all, we'll import CV2. Then we'll loop over I equals to 1 while I is less than 5. Image equals to CV2 dot IM read string I plus dot PMP image2. So this will read the image. Now we'll resize it. So we'll resize the image to 60, 60 because we don't want very big images. So let's print the initial size also. Image dot size initial size of image is and we'll print the final size also, which should actually be 60, 60. And in the end we'll save those images. And we'll save them by this. So let's run. Okay, we had to write I plus 1 also. Okay, yeah, so it's done. So yeah, CV2 has successfully saved the images. So yeah, so as you can see, we successfully have 4 new images which are of new size, that is 60, 60. So we'll be using these for as our positive images. Welcome back. So once you are done taking the original pictures, cropping them, and then resizing them using the script that we just learned, and you'll have these kinds of images which are now resized to 60 pics. Though I'll suggest you to do with multiple pics. The more pics you do, the better it would be for your learning algorithm, the easier it would get. And then we have also created negative images. But what you'll observe is many of the pictures in our negative images have these kinds of images. So what we need to do next is remove all these images. Though since these are negative images, though even if we use these images, it won't affect us much, but still we don't want to risk, like we don't want our learning, since they are in like good proportion, we don't want our learning algorithm to assume that these will always be there, though they'll be like very less. So let's delete all these images. Okay, so once we are done clearing all these images, what you need to do next is you need to go to this link, which is github.com /SAUHAARDAC /Haar training. So once you're here, what you need to do is you'll find a clone or download option, which is, okay, just a minute, let it load. Yeah, once you're here you will find a clone or download option. What you need to do is download the zip file. So it will take some time to download that zip file. Let it download. We'll be using this file to create our own Haar cascade. Okay, so once you are done downloading these zip files, what you need to do next is you need to go to the location where you downloaded these files and extract this. So we'll be using this extracted part, this one, for training our own custom Haar cascade. So now is the time that we have been eagerly waiting for. So now we'll be training. For that, first of all, you need to go to training and then you'll find hardtraining.bat, which is this, and now you need to edit it. So you will find this. So I'll tell you what all exactly you need to edit. First of all, you need to make sure that this file is the one that went into vector folder, that we the before we created the vector here, this vector folder. So it's face vector.vec, as you can see. So let's go back and check. So yeah, it's face vector.vec. The next thing that we need to look at is after making sure that this is right, then we'll change n pos to the number of positive images and n negative to the number of negative images. So we have a total of 8 positive images and the negative images is 1078. So I'll change it to 1078 and 8. This is the number of stages that we want. Ideally it should be between like 5 to 10. Like the more you and the more you enter, the better the classifier will become, but it will take longer. I don't have much of RAM and all, so I'll be training it just for like 6. This is the RAM in MB that you want to use. It should either be, it is suggested it should be like 512 or 1024. Then this will be the size of image, that is 60, 60. And then you'll just save it and just check it again. Looks like everything is fine, so we'll close it. The next thing you need to do is go to this cascades folder and delete everything, and then you need to run this file, which is hardtraining.bat that we just edited. So it ran fine, and as you can see, okay, let's check. Okay, I'll run this again. Run. Okay, ideally it should create folders here. Let's check if we have made any error in this. Hardtraining.exe -sec vector backslash face vector dot vec. Okay, this is fine. Negative backslash bg dot text. I'll run this again once. Okay, it's not 1078. The number of images is 2 less than that. That was the issue. As you can see here, you'll find these two files here also. So the number of our images is actually 1076. So that was the issue. So I'll just change it to 1076. I'll save. And let's try running this again. Okay. Why is it not creating folders? Ideally it should create folders here. Okay, let's check this again. Edit. There must be some issue here. Negative backslash pg dot txt. The number of images is 1076. Number of positive images is 8. And stages is -6. Okay, let's check this. Okay, where did this minus come from? Yeah, I suppose it should be fine now. Let's run this again. So as you can see, it's running. It will take like quite a long time. It will take some time, and then what you'll see, the end result is there would be folders here. So in the next video, we'll be using those to generate a .xml file. Okay, so once you have downloaded the hard training master repo, so now let's start. We have the data prepared. Now let's start making training. So first of all, we need to go to the directory which has all the negative images. So I'll copy all these negative images. Yeah, and one more thing that I found useful, to delete all the negative images, like the ones which had blanks, you don't need to select manually. Just right click and then sort by size. So that would make sure that all the bad pics or the ugly pics are together, and you can directly sort them, directly delete them. You don't need to select those negative pics manually like this. Okay, so now let's copy all these. What you need to do is, you will find a folder called negative. You need to paste these here. And then after that you will find this create. And after that you'll find this create list function. You need to run that. So once it runs, you'll find that in this bg text file, in this one file, you'll have the names of all these pictures. After that, copy all the positive pics. We'll copy all these positive pics and we'll paste those in. Just delete these and we'll paste those here. Okay, once we are done with this, now the next thing we need to do is, we need to go to positive and we need to open this obj marker, object marker. We need to run this. So you will find it like this. So now what you need to do is, you need to make a square or a rectangle, press space and then press enter. So you need to do this with all the pics. So if like I did this wrong, I'll press any key other than space or enter. Okay, I did wrong, so I'll have to select again. Space and then enter. Okay, so once you are done with this, what you'll see is, in your info file, you'll find when you open this file, what you'll see is there are the names of those images and a number in front of them that will tell how many rectangles, how many objects are there that we need to identify, and then the coordinates. So we are like almost done with preparing the data part. We have like prepared this object marker. So if you wanted to stop marking images, you could like have just pressed escape and that would have saved the progress. So this is the final file that had all the names. So now we'll create a vector training set. So for that we need to go to trainings and we'll find a file called samples_creation.bat, which is this. So we need to edit this file, right click edit, just give me a minute, I'll show you. I'm not sure why is this so large. Now I'll tell you what all exactly we need to edit. We need to change the width. So our width of the image is 60. The height of our image is also 60. So first of all, make sure that we change these things. And in npos, we need to write the number of positive images. Okay, no, once we change the width and height, make sure that this width and height are at least like less than 80 so that our training algorithm does not take very long. So after that we'll save it and we can close this file. So once we are done with this, the next thing that we need to do is we need to run samples creation.bat, that is this file. So in vector there is a file, I'll just delete it for now and now I'll run this again. It will take some time. So once it ran, you see there's a file called face vector.vec. So now we'll be using this to for the training part that we'll be learning in the next video. So now our training is complete and we need to generate the XML file. So for that, when you go to Cascades folder, you'll find one or multiple folders depending on how much of training data you had. All you need to do is copy that and paste in cascade to XML data. Delete all the ones that were already there and paste your new one. After that, what you need to do is you'll find a file which is convert.bat, which is in cascade to XML itself. You need to edit it. So we'll right click and we'll edit. As you can see the file, in that what you need to do is you need to change the height and width of your image. For our image, the height and width was 60/60, and here you need to write, you can like choose your custom name, whatever name you want. I'll choose bottle cap detector, something like that. I'm using bottlecap.xml. You are free to choose whatever you want. Save and then cross it. So once you're done with this, you need to run this convert.bat. It will take not even a minute, and it will generate this bottlecap.xml file. So we have generated this XML document. This is our Haar Cascade file, and we can use this in place of face detector if we want, and that will, so we have finally made a custom detector. I hope you enjoyed this. Welcome back. So now we'll be applying our final XML bottle XML file that we just made, and then we'll be applying it for detection task. We'll be using a custom Haar Cascade. Using our custom, I've trained it for like very less dataset and for like quite less time, so I'm not sure if we'll get good results. But yeah, if you train it for long and on the last dataset, you'll definitely get very good results. Nevertheless, let's try. So first of all, we'll import required dependencies, which is numpy, and then we'll be importing CV2. So now we'll be loading the cascade. I've saved the cascade file as bottlecap.xml. So we'll make a cascade bottle CV2 dot cascade classifier, and the name that I've saved by is bottlecap.xml. So now we'll be loading a video. Cap equals to cv2 dot video capture 0. So this will capture our video. Now we need to start our loop. While true. So now we need to read our cap into our image. Cap dot read. Now we'll be converting that into gray. Color to, sorry, color underscore, yeah, I suppose it is, yeah, to gray. Okay, now we need to detect multiscale. So we'll be doing faces equals to a bottle cascade dot detect multiscale, and we'll be doing that over gray 1.3 and 5. Now we need to make a square or a rectangle in faces. I'm not like telling in very much detail because we have already covered this before. I think it was the first video where we covered with the Haar Cascade. So if you are like still confused, you can probably refer that video again to get a in-depth explanation. So now we are making a rectangle. Now we need to show cv2 dot I am show, and we'll be showing that image comma image. Now if and 0xff equals to part of q, then we want it to break, and in the end cap dot release and cv2 dot destroy all windows. So now I'm going to run this. So as you can see, it's running to detect a cap, but it's also detecting my hand as cap. Like it's not definitely sure what exactly it is. If you would have trained it for longer and on a larger data set, I suppose it would have worked better. But yeah, it's like decent, not as bad as I was expecting. Okay, so this is how we make a custom Haar Cascade and use it for detection task. I made it for bottle cap. You can make it for any object. I suggest that you have a larger, you make a larger data set with a larger number of positive images, and I trained it just for 5 loops. I suggest you train it longer and it would work like far better. I hope you liked it.